Alright, so today I'm gonna be explaining this important article, GNNDELETE, a general strategy for unlearning in graph neural networks. So this ICLR paper in 2023 is very important. Graph unlearning, which involves deleting graph elements such as nodes, node labels, and relationships from a trained graph neural network model, is crucial for real-world applications where data elements may become irrelevant, inaccurate, or privacy sensitive. However, existing methods for graph unlearning either deteriorate model weights shared across all nodes or fail to effectively delete edges due to their strong dependence on local graph neighborhoods. To address these limitations, we introduced GNNDELETE, a novel model-agnostic layer-wise operator that optimizes two critical properties, namely deleted edge consistency and neighborhood influence for graph unlearning. Deleted edge consistency ensures that the influence of deleted elements is removed from both model weights and neighboring representations, while neighborhood influence guarantees that the remaining model knowledge is preserved after deletion. So it updates representations to delete nodes and edges from the model while retaining the rest of the learned knowledge. So, removing data is insufficient to comply with recent demands for increased data privacy, because models trained on the original data may still contain information about removed features. A naive approach is to delete data and retain a model from scratch, but this can be prohibitively expensive, especially in large datasets. So recently, efforts have been made to achieve efficient unlearning based on exact unlearning. The core idea is to retrain several independent models by dividing a dataset into separate shards and then aggregating their predictions during inference. Such methods guarantee the removal of all information associated with deleted data. However, in the context of GNN, dividing graphs destroys the structure of the input graph, leading to poor performance node edge graph level tests. To address this issue, this reference uses a graph partitioning method to preserve graph structural information and aggregate predictions across individually retrained shards to produce predictions. However, this approach is still less efficient as the cost increases as the number of shards grows. So we introduced GNNDELETE, that is a general approach for graph unlearning that can delete nodes, labels, relationship from any trained GNN model. We formalize two essential properties: deleted edge consistency and neighborhood influence. So this is an illustration of deleted edge consistency. It suggests that predicted probability of deleted edges after unlearning should be random, such that it looks like the deleted data was not used for training before. And in B, here you see the neighborhood influence, illustration of neighborhood influence. It implies that an appropriate unlearning should not change the representations of local neighborhood nodes in the subgraph, not nodes themselves, to maintain the original causality. And finally, in C, we'll see the overview. Given a trained GNN model and edge deletion requests, GNNDELETE outputs unlearned representations efficiently by only learning a small deletion operator. So it also ensures representation quality by minimizing a loss function that satisfies the two key properties proposed above. So in message passing, we have aggregation, then we have updated. But unlearning is something new. Unlearning for GNN. To unlearn an edge, the model must erase all information and influence associated with that edge, as if it was never seen during training, while minimizing the change in downstream performance. So what is the problem? Given a graph and a fully trained GNN model, we aim to unlearn every edge from M, where E sub D is the set of edges to be deleted. The goal is to obtain an unlearned model that is close to the model output that would have been obtained had the edges in E been omitted from training. So we require these properties: deleted edge consistency and neighborhood influence. For example, in deleted edge consistency, if E is an edge, then M prime should output a prediction that is independent of the existence of that edge. So deletion of edge should not have any influence on the predicted output. The second property, neighborhood influence. So if edge is not in E, then M prime should output a prediction that is close to M. The deletion of edges should not have any significant impact on predictions in the rest of the net graph. So it also reminds me of robust graph neural network, which is another playlist. So what are the required properties for successful deletion on graphs? First, deleted edge consistency. As I said, we want to have the unlearned layer G prime satisfy the deleted edge consistency if it minimizes the difference between node pair representations of two randomly chosen P and Q, where phi is a readout function. Any P and Q, any random P and Q that you chose from vertices, the expectation over them should be very small. Remember that here E denotes an edge to be deleted, which has, for example, U to V. So this edge UV, we call it, this one has a representation for each of, for example, phi of U, phi of HU, and HV. So this edge has a representation. So node pair representations, so let's call it edge representation, they should satisfy this property. The second one is neighborhood influence. So we represented the neighborhood like this. And finally, the deletion operator. Now following the notation, the elf GNN layer with output dimension D prime, we define an extended GNN layer with unlearning capability. So deletion operator combined with G with the same output dimension D. So given an edge that is to be removed, del is applied to the node representation. Then we have local update. Defining an operator that acts only in the local neighborhood enables targeted unlearning, keeping previously learned knowledge intact as much as possible. If node U is within a local neighborhood of E, del is activated. So moving from layer-wise operator to the whole GNN, our method applies del to every GNN layer. So for the else GNN layer, we first compute the deleted edge consistency loss and the neighborhood influence loss. Neighborhood influence loss, deleted edge consistency. We combine them, it becomes our total loss. And they have some experiments for both node classification, which is one graph, many nodes, and graph classification, which has many graphs, but each graph is very small number of nodes, like 20, 30. And node deletion, you see the F1 score. They also did for link prediction. It's interesting, but it is very high. So the challenge is more about, for example, in F1 score, you see it's still 84. It is still below 95. It is 100 node deletion evaluated on node classification task. So you see other alternative models that are in the literature, very important. So this is the current paper. And graph convolution networks, you can, because your core could be any kind of model, so graph attention, graph isomorphism network,